Thank you, Chairman. Ladies and gentlemen, the title of my application, my presentation, Application Under FAIR++, Thermal Simulation in an Electrical Motor. The outline of my presentation, I start with the introduction. After that, I will talk about the geometry of the analyzed motor. And after that, I will present a few previous results that we do under Fluent and Abacus. And after that, I will talk about the motor losses, terminal analysis, heat source model, and the proposed or the planned method to solve this problem, and a few numerical results and remarks. The motivation of this work is that to prepare and to develop a thermal model for finding the temperature distribution of different parts of an electric motor during its various operating conditions. The motor temperature is closely linked to the life and the performance of the electrical motor. There are three types of thermal risks. The first one, the stator winding temperature can affect the winding insulations. The second, the winding resistance is proportional to the temperature. That means that the higher resistance will be equivalent to have a higher thermal losses. And another problem is in the rotor. When the rotor is very, very high, that can affect the efficiency of the permanent magnet, because the magnet is very, very sensitive to the demagnetization at elevated temperature. In order to avoid the overheating problem, heat generated in the PM motors should be transferred toward outside air, and it's essential to have a detailed knowledge of the heat exchange in the PM motor. The prediction of the temperature distribution in an operating electric motor is required at the machine design stage. Now, our motor, it's here. This is the prototype motor, and here it's the CAD model. And it's our motor, it's an exterior radial fluxes. That means that the magnets are located outside the winding, and the stator and the winding are difficult to cool. And the geometry of our motor is only enclosed, that you can see here. And the power of this motor is about 11 kilowatts. Here, a few photos. This is the stator and the winding part of our motor, and here it's the rotor. And here we have the magnet. And this part go inside of this rotor. And we do some measurement, and you can see the localization of our thermocouple to take the temperature of this part. Now here is exposed view of our motor. It's look like that. It's here the winding and the stator, and here is the rotor. The geometry of the rotor is a hollow cylinder, and it's a fixed stator, which is here. It's located within the rotating rotor. The stator slot is filled with one material only. It's here, it's the winding. This is the copper. And the winding region is modeled as solid region because here we have three material. We have the copper, we have the insulation material, and we have the area between the electrical part. And the head of our winding, it's modeled as torus. The calculation of this model, the thermal calculation in this model, we do that in Fluent Abacus under this, using this mesh. It was about 10 million. And here in red, this is the fluid part, or the air gap. And here we have a section of our air gap. It's very, here we have a very narrow places between the magnet and the stator winding, and here. I think the first will be the CFD computations. We use Reynolds average Navier-Stokes equation using turbulence method 2, and we impose a temperature in the boundary of the winding and stator, and we use approximately 5 million cells. Here we have the contour of the velocity, the contour of the temperature. Here, streamline obtained at this. And here we do that with very small rotations. Here, different view of the streamline obtained by Fluent. And in the solid part, we do the calculation with Abacus, and here we have the anchor motor, and here only the winding part. And you can see the difference between the two heads obtained by Abacus. Now, when we talk about thermal model, we need, in the motor, we need to talk about motor losses. Power losses in the PM motor are an important consideration, as they are dissipated in form of heat, hence they act as energy source in our computational thermal analysis. And we have some losses. The first one is the winding copper losses. This is a classical Joule losses, Joule effect. Is the product of the resistance of the square of the current. And we have other losses, core losses, which become for the eddy current losses and the hysteresis effect. I give here the formula to calculate this type of losses. We need the flux density and the frequency. In this calculation, in the first time, we don't take an account this for these losses. And we have other type, mechanical, from the fraction losses, the contact between a part, solid part of the model. Thermal analysis. Customary, we solve that using finite and in the motor, and the finite element, the coupled finite element, and the computational fluid dynamic analysis, which mean that we use finite element in the solid part and the CFD in the fluid part. And we need to do some communication between the two parts, and you see the hot fluxes come from the fluid, and the temperature as boundary condition come from the structure. And it's well known that the CFD is very complicated. We need use turbulence model to capture all effect in the interior of the motor. Now, conjugate heat transfer. I give here the equation because for FAIR++ we need to start from the model. Here we have in the solid part, the temperature have to satisfy this equation, and we have the second member of this equation is come from the electrical losses. And the second part in the fluid, here we plan to model with using incompressible Navier-Stokes equation with Boussinesq's approximation. And here they are the system that we have to solve. The continuity equation, the momentum augmented by the Boussinesq approximation, and the last equation we have the energy in the fluid part. Source of model. Here, how the method to calculate the losses in the motor. As I say in the 5th slide, we will calculate only the losses coming from the Joule effect. And for that, we use electrostatic model, which means that the electrical potential field in the conductor is governed by Maxwell equations. And this equation can be written in the steady state cases in this form. After that, we use the constitutive equations with a relation between the electrical field and the current density. And after that, we need the balance equation express the conversion of the charge. This is the Gauss law. It's written in this form. And after that, it's very easy to, using the previous equation, we obtain the Poisson equations. We need to solve this problem. We need a few boundary conditions. Here, prescribed electrical potential, and we can give, as Newman, the current. And after that, when we have the potential, we can calculate the Joule losses by these equations. Now, the proposed or the planned model to solve the thermal model in our cases look like that. In part, this equation in the solid part, these equations in the fluid part, and in the winding, we have to solve that to calculate the losses. And this is a very, very nonlinear problem, nonlinear coupled problem. To solve that, I don't go in the detail how to write the variational equation of each equation. I use a few notations. Here we introduce these notations, which the first component is the velocity and the pressure. It's coming from the fluid part. The term temperature is coming from solid and the fluid part, and the potential. The first problem, it's in the solid one. This is the potential. No, the first one is the fluid part. The second one is coming from the temperature, and the last one is coming from the potential. To solve this problem, nonlinear problem, customary we use Newton method, which look like that. we have to write our equation, the first order of the Taylor series. And here we have the first derivative, with, in this case, is the Jacobian of the matrices, and here the iteration functions too. And here we have a lot of zero because the dependence in the second we have only temperature and we have velocity too. We will have a lot of zero in this matrix. Now, the algorithm to implement, it's the customer algorithm. We start by to compute the Jacobian and the residual, and we have to solve that. And we have to do that, that's these two quantity, not the product. Yeah, these two quantities have to be small. And this is the planned algorithm to solve our thermal problem. Actually, I don't have implement that because I have some problems. But each problem, for example, the thermal, it's not difficult to implement that in the solid. The potential using fail ++ program, the potential too is not difficult to implement. But using this couplet problem, I have a small problem. I don't have a result about that. Now, the first numerical result. The first example, it's only we solve the conduction problem in the winding stator only because when I use the old model, which it's about more than 10 million cells, I have a problem with MPI. Actually, it don't work. But using my program, we can. It was able to using fail ++, able to calculate the temperature in the stator and the winding. The second, here I use a smaller model. Here, the dimension of our model is the same, but we use here coarser meshes because to solve the condition problem, we don't need very, very fine element. Here, it's the 8th of the domain. And we can see here we have rotor stator here, and here we have the gap, air gap, we have the magnet, and it's here. It was about 120,000 cells using fill. The same, but here we use I use the Carter of this model, the motor model, and we have the same compartment of our solution. And we have used here double number of the cell. Now, for the coupled conduction and potential problems, it was impossible to calculate the potential in the previous geometry, where we have only the winding and the stator, because I have a high gradient of the potential in when I calculate the potential in this geometry. And using this potential, we have very, very high temperature. Because this geometry it's not adequate to use for electrical method, for electrical problems. And I do another geometry when I drop the head of our winding, you can see here, without head, and they put the potential. Here we have the winding only, you can see. Here we have the starter, and here we have more. We have the air gap, we have the magnet, and we have here the support of the magnet. And you can here that's work correctly the potential calculations, and here it's here the potential in the other side, and here it's the temperature. The same with other value of the potential. And the last one example is a very small example, but here we can see we have a domain. Here we have a conductor part, here isolant part, and here we have at the middle the temperature is very, very high. And it was the last example. Thank you very much for your attention, and it's time for questions.